Okay. Now we can continue. We were seeing some famous processes of image processing. We have seen smoothing, sharpening. We have seen histogram and contrast operations as well. Now, let me briefly mention about one or a few nonlinear image processing examples, which are also known as stack order filters. When I give this kind of a name, the student may get terrified. What do you mean stack order and things like that? But when I say, for instance, median filtering, they tend to understand. But the filters, including median filtering, are actually doing a stack ordering first. So you have an image, okay, and inside an image you have a region, let's say 3x3 sliding window kind of region, and that is just a mask. You don't filter, you don't multiply every pixel over there with the corresponding filter intensity. There is no filter intensity yet, but while sliding you pick these 9 pixels and then you sort them in an ascending order or a descending order. Let's say ascending. So this will be the minimum value, and this will be the maximum value, and all the others are in an ascending order. If you pick the middle one, that would correspond to the median. Now, of course, you have to define the center position or the referring position of this sliding window. This is a 3x3 window, and let's assume that the center, the middle pixel, is the pixel that we are essentially replacing or processing. So at the output image, we are changing this the value corresponding to this red shaded small pixel position. We are just replacing at the output. We are replacing the value with this green shaded. Let me shade it by green, something like this. This is the input image, and this is the output image. When I do this kind of a process, this could be called a median filter. And this median filtering has some certain advantages over linear filters, like it helps us to eliminate speckled noises, like salt and pepper types of noises. If one of the individual pixels inside the image is extremely white or extremely dark, but it's just 1 pixel or maybe 2 pixels, a dot kind of a noise is appearing. These median filters completely remove that effect, because if it is, for instance, a salt type of noise, then its intensity will be within this range. If it is a pepper type of a darker noise, a few pixels, 1 or 2 pixels, it will be among the top range. So the pixel that we are changing will certainly be replaced with something more reasonable that is related with the neighboring other pixels. So those types of noises, the salt and pepper types of noises, are eliminated well. And since it is not really taking the average of some neighbors, first of all, the noisy one is not getting diffused like a point spread. If it's a pepper, for instance, it won't make the neighboring pixels darker. In linear filtering, that's what happens. We have that kind of a diffusion effect. And it also maintains the edges. of images. It doesn't blur the image, this kind of median filter. You can make it 3 by 3, 2 by 2, if you wish, but I wouldn't recommend an even-sized template. If it is 2 by 2 or 4 by 4, there will be an even number of elements, and the median value will be the average of the two middle values. Okay, so it is still an averaging operation that's going on, which has a blurring effect. So instead of 4 by 4, why don't you use 3 by 3 or even 5 by 5? Then there will be a certain middle value. There are some other filters that can be applied. If you want to, for instance, darken the image in an artistic kind of way, you can apply, for example, the minimum filter, min filter, which will just pick the darkest pixel among these 9 pixels and replace the center one with those. And the output image will look darker. Or if you choose the max, it would look brighter. These two things do not make much sense in continuous images like these, or gray leveled images. But in binary images, if you apply a minimum filter, that would correspond to an erosion. We will see that later, but I'm telling you already. And the maximum filter will correspond to dilation. Erosion is a shape, a white shape becomes a smaller white shape. And dilation makes a white with a black background, a white object shape, a larger one. That's what the minimum and maximum filters will correspond, and they will have certain names like erosion and dilation. They are also stack order filters in a sense, but stack order filters have one further advantage. They can be merged with linear filters, or sort of linear filters. Of course, the overall operation is perfectly nonlinear, but it may happen like this. You may make an ordering from the minimum to the maximum. I didn't count, okay. You may eliminate, for instance, the minimum or two of the minimums, and the maximum or two from those places, and you depict everything in between and apply some coefficients to these values. You multiply this one with A, this one with B, this one with C, D, E, F, for example. You multiply them as if you are doing a linear filtering. You multiply all of these with 1/6, for example. You take an average of those. Or you may favor the median value a little bit more. As you see, once you order them, you lose the coordinate information. So it becomes a time varying filter. It's not time invariant anymore, because the position, which one in this place, which is the red point in the center, which is the one that is right of it, we don't know. They are just shuffled and ordered in an ascending order. So the positions of these pixels in this list is unknown. And we just scale them, not according to the locations, as in linear time invariant filtering, LTI filtering, but we scale them according to their orders in this ascending or descending order. It's like the eliminated ones are actually scaled by zeros. These two, minimum and maximum, or a few from here and a few from there, could be considered as outliers. And elimination of the outliers is always, I mean, not always, but usually a good thing. They may correspond to these salt and pepper types of noise, for example. They may be too much extremes. In voting systems, for instance, usually these outliers are eliminated because they may correspond to a vote which is given by someone who hates that person or who loves that person. In both of those cases, the vote, the grade that he or she will give, will be unfair. So we eliminate them first, and the others we may take the average. in sports competitions, this is a very much useful thing, for example, and in image processing too. You can always get rid of the outliers first and do something else with the remaining. That is the advantage of using stack order filters. But the analysis of these are a little bit difficult because they are nonlinear and time varying mostly. But they are globally shift invariant because we are doing the same thing to the shifted location by a sliding window. So the shift invariance is not globally, but inside the local template that we are doing, things are a little bit shift invariant, not LTI. So their analysis or mathematical outcomes are difficult to analyze, but still there are mathematical tools where, for example, the median filter is the optimal, or the minimum or the maximum filters are optimal according to the noise that is contaminating the image or the signal. I'm terminologies that can also be used. It is called the mode. So there are three averaging techniques. One of them is the mean, the average that we know. We add up all the components and divide them to the number, and we find the average. That is the mean. The median is here. After sorting, we pick the middle one. That is the median. The mode is the one that is most commonly encountered in the list. So we count how many times a pixel is encountered. If, for example, 2 of the pixels are the same inside this 3 by 3 region, and all the others are different, the mode will be the value of these 2 pixels because they appear more than the other ones. Okay, the most populated in the population. That is mode. That can also be used in some cases, depending on your application. Okay, now another operation that is very popular is called, if you are familiar with, for example, Photoshop, and if you're keen on processing photographs to make them look better for the human eye, this is a terminology that you might have encountered. It is called unsharp masking. And if you don't know what it is, you may be scared of using it because the name is strange, awkward, unsharp. But this unsharp masking is actually a sharpening technique. It makes the image look sharper with better detail. How does it work? So unsharp is, masking is not a blurring operation. It is a sharpening operation, in fact. I will show you on an example profile. This profile you can think of as a slice of the image. So on the slice of the image, we have, let's assume, this kind of a profile. So somehow the right-hand side of the image is brighter and the left-hand side of the image is darker, and in between there is a transition which may be considered as some object, maybe at the right-hand side, and the left-hand side is the background. So this thing is visual. Okay, it's a profile. I'm showing it on 2 dimensions. Sorry, on 1 dimension as a graph, because the other 2-dimensional illustrations would be difficult for me to draw. First, by the way, this is the original image. It contains, by the way, it's very sharp, as you see. The changes are abrupt, and it's all there. But if you want to make it to look visually better, what you can apply is called unsharp masking. So you start from this profile of 1, and you apply first a low-pass filter. So you low-pass filter 1 and call it 2. Now, this is 2. What would it look like? I will try to draw it, illustrate it like this. So it's blurred a little bit, as you see. It's smoothed out. The transitions are not as sharp as this one, and there's a low pass filtering operation that is going on. By the way, I can draw the original on top of it, if you wish. So the red dashed is the original, and the black is the low pass filtered version. Let's call it 2. Then I obtain 3 as 1 minus 2. So I subtract the low pass filtered version. What would it look like? Let me draw it in a different color. Here on the towards the left hand side, 1 is larger than 2. Sorry, excuse me. The red one is 1, therefore 1 is less than 2. And 1 minus 2 would make something negative. It will probably look like this. And towards the right hand side, this time 1 will be greater than 2. So the difference between the low pass filtered and the original ones will look like this green profile, sort of. And I'm going to denote it as, I'm going to call it 3. Now, we will have the final thing, which is actually, let's call it 4, is equal to 2 plus a fraction of 3. Something times 3. 3 is the difference, as you see. By the way, if I pick lambda is equal to 1, then it will be 2 plus 3. And from here, you can see that 2 plus 3 is equal to 1. So 4 will be equal to, exactly equal to 1, the one at the top, if I choose lambda to be equal to 1. If I choose lambda less than 1, then it will be something between 1 and 2. It will be slightly blurred. But what happens if I choose lambda greater than 1? Then the situation will be an exaggeration, like this. Okay? Of course, this is only if lambda is greater than 1. If lambda is equal to 1, it would be the ideal, the first profile that we have. But if lambda is greater than 1, we add more of this green ripples onto 2, which will overshoot the effect. This overshooting effect, as I can see from the profile, is essentially not really sharper than 1. So 4 is not really sharper than 1. But when you apply it on a photograph and look at its effect visually, you will see that the edges, the abrupt changing places will be exaggerated a little bit, which looks like a sharpening effect. It doesn't contain more information. It's not more useful, but it looks better because the edges are emphasized a little bit. And whenever the edges are emphasized, the photograph that you look at looks sharper. And you may make some blind tests of applying this unsharp masking as opposed to the original photo. You will see that you start liking the unsharp masked photograph more. It looks more pleasing because it looks sharper. The edges are more emphasized. This is a trick that nowadays all the smartphones are using in their photo taking applications. Even without doing any process, they already process with some slight amount of unsharp masking to make sure that the photograph that you take, the picture that you take, looks pleasing to you. You think that, oh, the camera is excellent. It doesn't really resolve those pixels. It's not really that sharp, actually, in theory, but it looks sharper. So this is a basic kind of operation that I recommend you to take a look at. And if you like photography, then please apply this to some of your photographs, digital photographs, and try to see what's happening. There are two parameters in unsharp masking in Photoshop, for example. One of them is the filter width. So the low pass filter that you apply from 1 to 2 is a low pass filter, and it has a blurring template size. That size is known as the radius. That radius of the disk shape with which you are blurring, convolving, is one parameter of unsharp masking. The other parameter is called the lambda that I'm saying here. How much are you contributing? So adjust those things, and at some point you will see that some of the pictures actually look better at some scaling factor, of course. If you zoom all the way to the original size, it may not look sharp, but when you shrink down to fitting into the screen, onto the screen, for instance, it looks very sharp, it looks very nice. And you may prefer that before putting your photographs on social media, let's say. So this is a nice filter in that sense. It's not very useful for further computer processing. We don't want unsharp masked images for image classification and things like that. As you see, it's distorted actually. All right, now another page. Let's continue with our discussion. We are a little bit speeding up. Root filtering is the next thing that I want to talk about. And this kind of thing, the root filtering is trying to apply linear methods like linear low pass filters or high pass filters, etc. Some filters to have a nonlinear effect. And that nonlinearity is like we want to emphasize higher frequencies to make them look sharper, for example, emphasizing the high frequencies. And there are some tricks to do that. Because of the general characteristics of the Fourier transform or the spectral representation of a signal. Most of the signals that we have are naturally low-pass signals, like the images that we see or the audio that we listen to. So when you, for example, take the Fourier transform of an image, we see that at the center corresponding to the DC coefficient, there is a huge energy accumulation, and the high frequencies are smaller. So how can we emphasize those higher frequencies by looking at them in the Fourier domain? We can do this, for example. We first take our image and transform it. It can be a Fourier transform, it can be a discrete cosine transform. DCT is quite versatile here because it's real valued, and obtain V. This V, if it is discrete cosine transform, it would be real, but if it is Fourier transform, then it can be complex. And in general, let's assume that it can be complex, but you will notice that I'm not doing anything to the phase. So the complexity is not an issue here. We're talking about the magnitudes. So V, KL, what's happening to the pencil? Sorry about this. V, KL, this thing is consisting of a magnitude of V, KL, and a phase. Let's call it theta KL. Okay, at the KL position, this is the angle of VKL. Let's call it theta KL. Now, this thing, the magnitude, is usually small. For high frequencies, because of this phenomenon that I have explained to you. That's mostly an encountered situation. If I do something like this, VKL to the power alpha, okay, and I'm not changing the angle. But this alpha is something between 0 and 1. So it's like I'm taking the square root. For example, if alpha is equal to 1 over 2 or 0.5, then this power to the alpha is actually a square root operation. Now, for small values, when you take the square root, the value actually enlarges. If the value itself of VKL is less than 1 in magnitude, when you take the square root of it, it becomes larger. For example, what is the square root of 1 over 4? The square root of this is 1 over 2, which is a larger number. But if the value is large, like if it is 4, then the square root becomes 2. It becomes smaller. So this operation suppresses the larger values, meanwhile boosting the smaller values. It's just by putting a power of alpha. And when you do that, therefore the high frequency samples are emphasized. I didn't do anything, you see. I just took the Fourier transform and wrote it in the polar coordinates, like the magnitude and the angle. And I put, or I took the magnitude to the power of alpha, and it works. It is just doing some sharpening, some amount of pleasing kind of an operation. Another alternative, so this was alternative number 1. Another operation that you can do is to use logarithm, but it may be something like the logarithm of 1 plus magnitude VKL. And I'm not changing the phase, theta KL. This theta KL shows or indicates the shapes, the transitions, and it is that since it's not changing, the edges, the shapes that we see on an image, the thing that we see on an image does not really change. Okay, we're not allowed to change the angle, because when you change the angle and take the inverse Fourier transform, the time or space signal that you will get will be completely different. It will not be corresponding to the image anymore. But if you process the magnitude part, then that process will only affect the contrast, okay, the intensities and things like that, and it will not change the image to another image. When you do it like this, we notice that the logarithm 1 plus x looks like this. So for small values, the small values are emphasized, but large values are suppressed. Similarly, so smaller VKL will give you a relatively boosted, larger magnitude at the output. But if VKL is very large, logarithm of that will not be so large. Logarithm is a suppressing function. It's a suppressing operator. This also does the same thing. High frequencies are emphasized. Again, if you do something like this. By the way, when you take the logarithm and say that this thing, let's give a name to it, is equal to, what kind of a name can I give? From U to V, it's the Fourier transform. This is from V to, let's say, S, okay, S. We know that V is called the spectrum So from U to V to S is what we have. This V is called spectrum. But if you apply the logarithm, you will come up with S, which has a name, but it's just a terminology. So when you encounter that terminology, you will know that actually it's the logarithm taken version of the spectrum. And the first 4 letters are flipped around and called capstrum. So capstrum is the logarithm of spectrum. You can think of it like that. If you do filtering in the spectrum, it is called filtering. If you do filtering in the capstrum, if you further process the capstrum with some filters, the overall effect is called liftering. It's again flipping around, this time the first 3 letters. And I'm telling you these to give you an idea about what you can do in images. Because knowing your signal or focusing or getting deep into the behavior of the signal that you have in the Fourier domain, in the spectrum domain, or in time domain, will greatly help you to come up with ideas. Image processing is, the modern application of image processing is like 5% science and 95% art. And the art comes from here. It comes from intuitions. You look at it. Of course, you use mathematics. It's not those intuitions are not blind or completely artistic intuitions, but it is something that you are aware of. You should be aware of your mathematical tools. Look at the thing that you are doing, and you notice that, for instance, you want to emphasize the high frequencies. So the scientist which developed this kind of liftering, this is also analogous to another terminology which is called homomorphic filtering. You have to check their nuances, the slight differences from internet. But the scientist who has developed this was thinking in mind that I have to boost the high frequencies because that's what I want to do. How can I do that? These are the concave down functions, which is square root. Square root is a concave down function. It has this shape. Logarithm has this shape. So let me apply those things into the magnitude. Let me not change the angle, because if I change the angle or the phase, then the image is completely broken. We cannot do that. So after Fourier transform, let me take the magnitude and work on it with these concave down functions, and then take the inverse Fourier transform and see what's happening, what has happened. And it will help me to resolve my problems. Now I will show you another application of utilization of these, utilization of homomorphic filtering or liftering or capstrum in general. It is, let me say, this is the third thing. I'm not going to use any new thing, but I will use the logarithmic process like this. Suppose you have x plus noise, okay? This was a bad one. Let me try to draw it again. Okay, let me just say n. N is noise. Noise. And this is image. The way to get rid of this noise in terms of optimization is to use linear filtering. If depending on the noise distribution, if the noise, the additive noise is Gaussian, for example, you apply a Gaussian shaped low pass filter. A Gaussian filter would statistically best in terms of eliminating the noise, at least using linear methods. There are, of course, there may be nonlinear methods for tracking the noise. If the noise is not completely random, but if it has some noise process of its own, you may try to track it using Kalman filtering and things like that. That's possible. Conversely, if the noise is not Gaussian, but more heavily tailed, that's what we call a salt and pepper type of noise, then utilization of a median filter will be okay. But what if the noise is like this, x times n? So the noise is a multiplicative noise. Okay. Or even for this one, you can think of a convolution type noise. So you have X convolution with noise. Convolutional noise. If it is a convolutional noise, then by the way, in the Fourier domain, it will be multiplicative noise, right? So it becomes multiplicative in the spectrum, in the frequency domain. For this one particularly, utilization of capstrom instead of a spectrum will help me do this. Logarithm of x times n is logarithm of x plus logarithm of n. So when you take the logarithm, multiplicative spectrum or spectra becomes additive. So I can use additive techniques. The techniques that I mentioned about in the beginning, right? If there is additional noise, because if there is additional noise in the time domain or in the space domain, then in the Fourier domain, it also becomes additive noise. And we will be using some noise elimination techniques, including inverse filterings like Wiener filter, or if the noise has a structure, then it may be a tracking noise tracker like Kalman filtering and things like that. But they only work for additive noise. So how do we make a convolution noise in time domain or in space domain look like an additive noise in the spectrum domain? We take the logarithm of spectrum and it becomes multiplicative noise. Okay, so knowing your problem and knowing the mathematics which may fit to that problem is critical in image processing. Because the rest of the tools that you will be doing as engineers or as scientists for solving problems of real people from the industry or from military, from biomedical, whatever, you will be doing engineering, you'll be doing signal processing, you'll be doing image processing. And the way to do it, the way to apply it is to focus into the problem and see what's happening. You have the tools for that and think smart, solve the problem. The rest of them, the rest of the issues are available as toolboxes. There is OpenCV, for example, which has everything inside. Previous hour, I told you to write a histogram equalization or histogram calculation kind of programs in MATLAB, for example. And in MATLAB, there is actually histogram equalization. But you will notice that the histogram equalization in MATLAB does not work the same way that we have been talking about, because it's considering the so-called bin size, the delta width. So it's not really pixel by pixel considering histogram equalization. You have to choose the bin size to be equal to 1 pixel to make the MATLAB's original histogram equalization to be exactly the histogram equalization that we are talking about. So these are available as toolboxes, but you have to understand and know that you need to use histogram equalization here because the contrast is too shallow and we're not sure about the curves, where to apply the curves. So let's make it automatic. Let's take a region of a low contrast region and take the histogram equalization of that region and show it to the doctor, to the radiologist, and probably he or she will be seeing the tumor, for example, or the disease, whatever, in that biomedical image in a better way. So you have to know and understand what to use and what to apply. Otherwise, application of those things are in the toolboxes and they are available. Of course, I don't want you to use them. I want you to design them or to write them. By the way, a friend of yours has asked if you could write the histogram generation and equalization routine in Python or something like that. And well, of course you can do that. I have to agree because you may not have MATLAB. Maybe you may or you may not, depending on which school you're studying at. Maybe MATLAB is not available to you. If it is available, it's easier to use, so I would recommend that. But if it is not available, you can write it in Python. And since I don't currently have the compiler or the interpreter of Python for the time being in my tablet, I will, of course, ask you to plot or draw the outputs on your exam papers as well. Because for MATLAB, I will be able to repeat the experiments, but for Python, I don't think I will be able to repeat them. So please draw your outputs too. Okay, now it's already 11:53, so we are approaching to 12 o'clock. I can stop at this point. I talked a lot about the arts of these things. We will continue with some further discussion regarding these, what to use and when to use and how to approach the problems and things like that next week. So next week will be a critical, as usual. All the courses are critical, but next week will also be quite an important one. I will try to show you how to reconstruct some suppressed or lost parts, components, information of the image. That is more into, of course, there is very few things to do for enhancing the image. The things that we have seen up until now were enhancing the image for human perception. So they are not really enhancing the image. But there are, of course, problems where you really have to enhance the image because some parts are lost. So how can we reconstruct? Okay, reconstruct the image. There are ways to do it. It's not as easy as it looks in the CSI series that you see on the television, where a blurry image comes in and then the hacker over there writes a few lines and then on the screen, after some iterations, it becomes extremely crisp and sharp. Of course, it doesn't work that way, but somehow there is something actually close to those things. And we will see that. And it will be fun to see some of these things. But unfortunately, they will be, of course, mathematical, as you already suspect, because we are trying to reconstruct the information that is lost from other side information. We are trying to reconstruct those things. And how can we do that? Let us see next week. Up until then, we can stop at this point. I can stop the recording. If you have any questions regarding the things that we have seen until now, you may ask. I'll give you a few seconds to ask. Otherwise, I will stop the recording and leave you until the next week. So I'm waiting. No one opened the mic. There's no question on this chat screen. So I'm stopping. See you next week. Bye-bye.